Right now, your atoms are being pulled apart by a force that cannot be stopped. Every second that passes brings you closer to a moment that will erase everything. Your memories, your planet, the stars, the very concept of existence itself. Scientists believed we had trillions of years. They were wrong. A new calculation has shattered that comfortable timeline. The universe's death sentence has been accelerated. The end is not a distant abstraction for civilizations unimaginably far in the future. It is rushing toward us faster than physics predicted, and there is nothing anyone can do to prevent it. The revelation came from a team of physicists examining the fundamental properties of the Higgs field, the invisible ocean of energy that permeates all of space and gives particles their mass. What they discovered was not reassuring. The Higgs field, the very foundation upon which reality is constructed, exists in a state of profound instability. It is not resting in its lowest possible energy configuration. Instead, it occupies what physicists call a metastable state, balanced precariously like a boulder on a cliff edge, waiting for the slightest disturbance to send it tumbling into the abyss. When that collapse occurs, and the mathematics suggests it is not a question of if but when, the consequences will be absolute. A bubble of true vacuum will nucleate somewhere in the cosmos, expanding at the speed of light, obliterating everything in its path. There will be no warning, no evacuation, no final moment to say goodbye. One instant you exist, the next you are erased at the most fundamental level, your constituent particles reorganized into configurations that cannot support the chemistry of life, the physics of stars, or the geometry of spacetime as we understand it. The new calculation emerged from the laboratories of physicists studying quantum field theory and the standard model of particle physics. Using updated measurements of the Higgs boson mass from the Large Hadron Collider and refined calculations of the top quark mass, researchers constructed models of how the Higgs field behaves across different energy scales. What they found contradicts the comfortable narrative we told ourselves. Previous estimates suggested the Higgs field would remain stable for 10 to the power of 100 years, a time scale so vast it rendered vacuum decay a theoretical curiosity rather than an immediate threat. The new models tell a different story. When you account for quantum corrections with greater precision, when you incorporate the latest measurements from particle accelerators, when you properly calculate the tunneling probability through the energy barriers separating our current vacuum from the true vacuum, the timeline compresses dramatically. Some calculations now suggest the Higgs field could undergo catastrophic decay in as little as 10 billion years. Others indicate timescales even shorter under certain cosmological conditions. 10 billion years still sounds like eternity to a species that measures its existence in mere thousands of years. But cosmologically, it is tomorrow. The universe is currently 13.8 billion years old. 10 billion years from now represents a moment less than twice the current age of the cosmos. Stars will still burn, galaxies will still form. Life, if it evolved elsewhere, could still be flourishing across billions of worlds. And then, without warning, a sphere of annihilation will appear somewhere in the observable universe and begin its inexorable expansion, consuming everything. The death will spread at light speed, meaning no information about the approaching destruction can ever outrun the destruction itself. Civilizations will be obliterated before they detect even a photon of warning. One moment, intelligent beings will be contemplating their futures, building their technologies, loving their children. The next moment, they will cease to exist in any meaningful form as the fundamental constants of physics rewrite themselves and render their atomic structures impossible. But the horror deepens when you understand what metastability actually means. The Higgs field is not unique in its precarious position. Other quantum fields that define the properties of particles and forces may also exist in false vacuum states. The electromagnetic field, the strong nuclear force, the weak nuclear force, each is described by quantum field theory, and each could potentially occupy a metastable configuration. If one field collapses, it could trigger a cascade. The Higgs field decay might destabilize other fields, creating a runaway process that rewrites the entire structure of physical law. The universe that emerges on the other side of this transition would be utterly alien. Atoms as we know them could not exist. The forces that bind quarks into protons and neutrons might strengthen or weaken beyond recognition. chemistry would become impossible. The stable matter that forms planets, stars, and living organisms would disintegrate into exotic particles that cannot combine into complex structures. The mathematics behind this cosmic death sentence lies in quantum tunneling, one of the strangest predictions of quantum mechanics. In the quantum realm, particles do not need to possess enough energy to climb over an energy barrier. They can simply appear on the other side through a process that has no analog in classical physics. Imagine rolling a ball up a hill. In classical physics, if the ball lacks sufficient energy, it rolls back down and remains in the valley. In quantum mechanics, the ball has a small but non-zero probability of suddenly materializing on the other side of the hill without ever climbing over it. This is tunneling, and it occurs constantly at subatomic scales. Electrons tunnel through barriers in the transistors powering the device you are using to read these words. Tunneling enables nuclear fusion in the cores of stars, allowing protons to overcome their electromagnetic repulsion and fuse into heavier elements. The Higgs field can tunnel too. Currently, it sits in what we call a local minimum of its potential energy, a valley in the energy landscape. But quantum field theory suggests there may be a deeper valley, a configuration of the Higgs field with lower energy. The Higgs field cannot simply roll from its current position to the lower state because an energy barrier separates them. A quantum hill too steep to climb without an enormous energy input. But the field does not need to climb. It can tunnel. At random points in space, quantum fluctuations can cause a small region of the Higgs field to spontaneously jump to the true vacuum state. This creates a bubble. Inside the bubble, physics operates according to different rules. The mass of particles changes, the strength of forces changes. The geometry of space-time itself may change. And the bubble expands. The boundary of the bubble, the domain wall separating true vacuum from false vacuum, carries enormous energy density. This energy propels the bubble outward at nearly the speed of light. As it expands, it converts more false vacuum into true vacuum, growing without limit until it has consumed the entire observable universe. The probability of this tunneling event occurring is extraordinarily small at any given point in space and time, but the universe is extraordinarily large. Our observable universe contains roughly 10 to the power of 80 atoms spread across a volume with a radius of 46 billion light-years. Even an absurdly tiny probability becomes inevitable when multiplied across such incomprehensible scales. The question is not whether a vacuum decay event will occur, but when. And the new calculations suggest the when is much sooner than we hoped. To understand how physicists arrive at these timescales, we must examine the energy landscape of the Higgs field in detail. The Higgs potential, the mathematical function describing how the field's energy depends on its value, determines whether our vacuum is stable, metastable, or outright unstable. Early measurements of the Higgs boson mass at the Large Hadron Collider in 2012 revealed a value of approximately 125 giga-electron volts. This mass, combined with the measured mass of the top quark, the heaviest known elementary particle, determines the shape of the Higgs potential at high energies. When physicists calculated the Higgs potential using these masses, they discovered something troubling. At low energies, the energies relevant to everyday physics and chemistry, the Higgs potential has a nice, stable minimum. The field sits comfortably in this minimum, giving particles their observed masses. But when you calculate the potential at extremely high energies, energies that existed only in the first moments after the Big Bang, or perhaps in the cores of colliding black holes, the shape changes. The potential develops a second minimum, deeper than the first. This means our current vacuum state is not the lowest energy configuration. We live in a false vacuum, a metastable state that will eventually decay to the true vacuum. The question that determines our fate is how thick the barrier is between these two minima. If the barrier is tall and wide, tunneling is exceedingly unlikely, and the false vacuum can persist for timescales that dwarf the current age of the universe. If the barrier is thin or low, tunneling becomes probable on cosmologically relevant timescales. The thickness of this barrier depends sensitively on the precise values of the Higgs mass and the top quark mass. Small changes in these parameters dramatically affect the stability calculation. This is why physicists at the Large Hadron Collider measure these masses with obsessive precision. Every additional decimal place of accuracy in the Higgs boson mass translates into dramatically different predictions for the lifetime of the universe. The latest measurements, combined with sophisticated quantum field theory calculations that account for higher-order corrections, paint an increasingly worrying picture. The barrier appears thinner than earlier estimates suggested. The tunneling probability is higher. The expected lifetime of our vacuum shrinks with each refinement to the calculation. Multiple research teams have published analyses reaching similar conclusions. A 2018 paper by Espinosa, Judy K., and Riotto recalculated the Higgs potential using improved measurements and found that the electroweak vacuum is metastable, with a lifetime that could be as short as 10 to the power of 10 years under certain assumptions about quantum gravity corrections. A 2020 analysis by Bednyakov and Kniel incorporated even more precise measurements and concluded that while the vacuum is most likely metastable, the uncertainty in top quark mass measurements still allows for the possibility that we live on the edge of absolute instability. In 2022, researchers at King's College London published calculations suggesting that vacuum decay could be catalyzed by primordial black holes, dramatically reducing the expected lifetime if such black holes exist in sufficient numbers. The catalytic effect of black holes represents a particularly disturbing possibility. Black holes warp spacetime so severely that quantum field theory behaves strangely in their vicinity. Near the event horizon, the intense gravitational field can provide the energy boost needed to help the Higgs field tunnel through the barrier, separating false vacuum from true vacuum. Primordial black holes, hypothetical black holes that formed in the early universe from density fluctuations rather than stellar collapse, could be scattered throughout the cosmos. If they exist, they act as potential nucleation sites for vacuum decay. Each primordial black hole becomes a ticking time bomb, a location where the probability of catastrophic tunneling is enhanced. Recent observations from gravitational wave detectors like LIGO and Virgo have not detected unambiguous evidence for primordial black holes, but they have not ruled them out either. If even a small population of primordial black holes exists in our universe, the lifetime of the false vacuum could be dramatically shorter than calculations based on spontaneous tunneling alone would suggest. The universe does not care about our preferences. It operates according to mathematical laws that feel no obligation to preserve structures that happen to support conscious observers. The Higgs field is not deliberately stable or unstable. It simply exists in whatever configuration minimizes energy, and if that configuration happens to be incompatible with our continued existence, that is not a moral failing of the universe but simply a fact of physics. We are accustomed to thinking of natural laws as eternal and unchanging, the bedrock upon which all structure rests. But quantum field theory teaches us that what we call natural laws are emergent properties of underlying quantum fields. If those fields change, the laws change. Vacuum decay is not the destruction of matter within a universe governed by fixed laws. It is the destruction of the laws themselves, the wholesale replacement of one set of physical principles with another. What would actually happen during a vacuum decay event? The process would begin with quantum fluctuation, a random event occurring at some point in space and time. In a region roughly the size of a proton, the Higgs field would spontaneously tunnel from its current value to the true vacuum value. This creates a bubble of true vacuum embedded in the surrounding false vacuum. The boundary of this bubble, called a domain wall, carries enormous energy. The exact energy depends on the difference in energy density between true and false vacuum and the thickness of the transition region, but calculations suggest values ranging from billions to trillions of times the energy density of an atomic nucleus. This is not merely hot, this is energy density comparable to what existed in the first microseconds after the Big Bang. The domain wall accelerates outward. Unlike explosions in conventional physics, which slow down as they expand due to friction and energy dissipation, the vacuum decay bubble maintains its speed because it continuously converts false vacuum into true vacuum, releasing energy that drives further expansion. Within nanoseconds of its formation, the bubble wall is traveling at 99.9999% of the speed of light. From the perspective of observers in the false vacuum, the approach is undetectable until the moment of impact. Light from the expanding bubble wall cannot outrun the wall itself. There is no warning, no signal. The universe appears perfectly normal, right up until the instant the bubble wall arrives and rewrites the fundamental constants of nature. What happens at the moment of crossing depends on how different the physics inside the true vacuum is from our current false vacuum. In the most optimistic scenario, the true vacuum has parameters close to our current values. Particle masses change by small amounts. Force strengths shift slightly. Chemistry is disrupted but not destroyed. In this case, the passage of the bubble wall would be violent but not absolutely lethal. Structures would be torn apart by the energy density of the domain wall, which would appear as a blast of radiation intense enough to vaporize planets and stars. But after the wall passed, matter could potentially reform into stable configurations, albeit configurations governed by slightly different physical laws. This scenario, while catastrophic to any existing life and structure, would not represent the true end of complexity in the universe. The more likely scenario is far worse. Calculations suggest the true vacuum may have a Higgs field value very different from our current value. Inside the true vacuum, the Higgs mechanism that gives particles mass could function completely differently. Quarks, the constituents of protons and neutrons, might become massless or acquire masses hundreds of times larger than they currently possess. The electromagnetic force could strengthen or weaken by factors of 10 or more. The strong nuclear force that binds atomic nuclei together might no longer be strong enough to hold protons and neutrons in stable configurations. In this scenario, atoms as we know them cannot exist. Protons would decay or fly apart. Electrons would not bind to nuclei in stable orbitals. The chemistry of carbon, oxygen, nitrogen, and all the elements that make up living organisms would become impossible. But even this understates the catastrophe. The true vacuum might have such different properties that spacetime itself becomes unstable. General relativity tells us that matter and energy curve spacetime, creating the phenomenon we call gravity. But the specific relationship between matter energy and spacetime curvature depends on constants that are ultimately determined by quantum fields. If the vacuum transition changes these constants dramatically, spacetime could respond by collapsing into black holes or expanding into disconnected regions that can never again communicate. The causal structure of the universe, the very notion of events occurring in sequence and objects existing in definable locations, could break down. The universe inside the true vacuum bubble might not be a place at all, but a mathematical abstraction that cannot support any structure we would recognize as physical. The domain wall itself represents a phenomenon unlike anything we can experience in ordinary physics. It is not made of matter or energy in the conventional sense. It is a discontinuity in the Higgs field, a region where the field transitions from one value to another over a distance comparable to the quantum wavelength of the Higgs boson. This distance is unimaginably small, roughly 10 to the power of -16 centimeters. To put this in perspective, if an atom were the size of Earth, the domain wall thickness would be smaller than a human hair. Yet this infinitesimally thin boundary carries energy density exceeding that of atomic nuclei. The wall is a knife edge in spacetime, cutting through the universe and separating two incompatible realities. As the bubble expands, it does not grow at a constant rate as measured by observers inside the bubble. Special relativity teaches us that time and space are relative, depending on the motion of the observer. From the perspective of someone outside the bubble in the false vacuum, the bubble wall approaches at nearly light speed. But from the perspective of someone inside the bubble, assuming they could somehow survive the transition, time behaves strangely. The intense energy density of the domain wall creates such severe spacetime curvature that relativistic time dilation becomes extreme. An observer at the center of the bubble would experience time passing normally, but they would see the distant universe outside the bubble frozen in time, as if the entire exterior cosmos had stopped. This is because the bubble wall is a kind of horizon, similar to a black hole event horizon, beyond which causal signals cannot penetrate in certain directions. The mathematics describing vacuum decay come from quantum field theory in curved spacetime, a framework that combines quantum mechanics with general relativity. The key equation is the tunneling probability rate, derived by physicists Sidney Coleman and Frank DeLucia in 1980. Their calculations showed that the probability per unit volume per unit time for a false vacuum to decay is proportional to the exponential of minus the action of an instanton. a solution to the field equations that describes the quantum tunneling process. The action is a quantity from classical physics related to energy and time, and the instant in action depends on the height and width of the energy barrier separating false from true vacuum. When the barrier is high and wide, the action is large, the exponential is tiny, and tunneling is incredibly unlikely. When the barrier is low or thin, the action is small, the exponential is closer to 1, and tunneling becomes probable. Calculating the instant in action for the Higgs field requires knowing the precise shape of the Higgs potential at all energy scales. This is where experimental measurements become crucial. The Large Hadron Collider smashes protons together at energies high enough to create Higgs bosons and measure their properties directly. Each collision produces a spray of particles, and by carefully analyzing the patterns in these sprays, physicists can extract the Higgs boson mass and other parameters with extraordinary precision. The current best measurement gives a Higgs mass of 125.25 giga-electron-volts with an uncertainty of only 0.17 giga-electron-volts. This represents a precision of better than 1 part in 1,000, an astonishing achievement for a particle that exists for only a trillionth of a second before decaying. But 1 part in 1,000 is not good enough when the consequences are the end of the universe. Small uncertainties in the Higgs mass propagate through the stability calculation and create large uncertainties in the predicted vacuum lifetime. This is because the Higgs potential depends on the Higgs mass raised to the 4th power at high energies. A tiny change in mass creates a much larger change in energy, which translates into dramatically different barrier shapes and tunneling probabilities. To truly nail down the fate of the universe, physicists need to measure the Higgs mass and the top quark mass to parts per million precision. This requires running the Large Hadron Collider for many more years, accumulating billions of collisions, and developing ever more sophisticated analysis techniques to extract parameters from the data. The top quark mass is equally critical because the top quark interacts most strongly with the Higgs field. In fact, the top quark is so heavy precisely because it couples to the Higgs field much more strongly than any other particle. This strong coupling means that quantum corrections involving virtual top quarks have an outsized influence on the Higgs potential at high energies. Current measurements place the top quark mass at approximately 172.76 giga-electron-volts, but the uncertainty is about 0.3 giga-electron-volts, significantly larger than the uncertainty in the Higgs mass. Improving this measurement is challenging because top quarks are produced much less frequently than Higgs bosons at the Large Hadron Collider, and their decay products are difficult to distinguish from background processes. Multiple theoretical uncertainties also plague the vacuum stability calculation. The standard model of particle physics is extraordinarily successful at describing the behavior of particles and forces at currently accessible energies, but we know it is incomplete. It does not include gravity. It does not explain dark matter or dark energy. It offers no insight into why the Higgs mass has the particular value it does rather than some other value. These missing pieces could dramatically alter the stability calculation if they become important at high energies. For example, if new particles exist with masses just beyond the reach of current colliders, they could modify the Higgs potential through quantum loops. Depending on how these new particles interact with the Higgs field, they could stabilize the vacuum, making decay impossible, or they could destabilize it, dramatically shortening the universe's lifespan. Supersymmetry, a theoretical framework that proposes every known particle has a heavier superpartner, could potentially stabilize the Higgs vacuum. If supersymmetric particles exist, their quantum corrections to the Higgs potential could cancel some of the destabilizing effects from top quarks and other standard model particles. This would raise the energy barrier, make tunneling less likely, and extend the vacuum lifetime to truly astronomical timescales. But experiments at the Large Hadron Collider have found no evidence for supersymmetry at energies up to several tera-electron-volts. Each year without a discovery makes it increasingly likely that, if supersymmetry exists at all, the superpartner masses are too heavy to save us from metastability. Other extensions to the standard model could go in the opposite direction, making the vacuum even more unstable. Extra dimensions of space, predicted by some string theory models, could allow the Higgs field to interact with fields confined to higher dimensional branes. These interactions could lower the barrier separating us from the true vacuum, dramatically increasing the tunneling probability. Some calculations suggest that if certain types of extra dimensions exist, vacuum decay could occur on timescales as short as millions of years rather than billions. The universe would still appear stable over human timescales, but cosmologically it would be on the verge of catastrophic collapse. The anthropic principle offers a strange kind of comfort in the face of vacuum instability. This principle states that we should not be surprised to find ourselves in a universe with properties compatible with our existence, because only such universes can produce observers. If the Higgs vacuum were absolutely stable or had already decayed to true vacuum, we might not exist to ponder the question. Metastability, from this perspective, is precisely what we should expect to observe. We live in a universe teetering on the edge of collapse, because only such universes have the right combination of stability and instability to produce complex structures like stars, planets, and conscious beings. Universes with completely stable vacuums might have different physics that prevents the formation of atoms or chemistry. Universes that have already decayed to true vacuum obviously cannot support observers. This anthropic reasoning does not change the physics. The universe will still decay eventually, but it suggests that the timescale for decay must be long enough to allow for the evolution of observers, which provides a lower bound on the vacuum lifetime. If intelligent life requires billions of years to evolve, as it did on Earth, then the vacuum lifetime must exceed billions of years in any universe where observers exist to measure it. This argument gives us reason to believe that the most pessimistic estimates, those suggesting decay on timescales of millions of years, are probably wrong, but it offers no protection against decay timescales of tens or hundreds of billions of years. Such timescales are long enough for life to evolve, but short enough to represent a genuine cosmic threat. Even if the vacuum lifetime is trillions upon trillions of years, far longer than the current age of the universe, the threat is not eliminated but merely postponed. In the long run, quantum tunneling is inevitable. The second law of thermodynamics guarantees that any system will eventually explore all accessible states given enough time. The Higgs field, spread across the vast volume of the universe, has countless opportunities to tunnel. Every cubic centimeter of space, every passing second, represents a chance for fluctuation that could nucleate the bubble of destruction. Multiply that tiny probability by the incomprehensible number of cubic centimeters in the observable universe, and the even more incomprehensible number of seconds in the far future, and certainty emerges from impossibility. In the unimaginably distant future, long after the last stars have burned out and black holes have evaporated through Hawking radiation, the universe will enter what cosmologists call the dark era. In this epoch, matter as we know it will have mostly disappeared. Protons will have decayed into lighter particles if certain grand unified theories are correct. Black holes will have radiated away their mass. The universe will be filled with nothing but a thin soup of photons, neutrinos, and perhaps exotic particles like axions or neutralinos if dark matter consists of such things. The temperature will be incomprehensibly close to absolute zero. Time will have lost most of its meaning because there will be almost no change, no processes occurring that could serve as clocks. But even in this frozen wasteland, the Higgs field will persist. Quantum fields do not evaporate or decay. They are fundamental aspects of space-time itself. And as long as the field exists in a metastable state, there is a probability for tunneling. In fact, the probability may increase in the dark era. With no matter around to stabilize the vacuum through finite temperature effects, with no energetic processes to disrupt quantum coherence, the field may be more susceptible to catastrophic fluctuations. The universe could survive for 10 to the power of 100 years, long enough for all conventional matter to disappear and all black holes to evaporate, only to be destroyed by a process that was waiting patiently in the quantum noise all along. The ultimate fate awaiting a universe that undergoes vacuum decay depends on the properties of the true vacuum. If the true vacuum has a cosmological constant, the parameter that determines the strength of dark energy, that is more negative than our current value, the consequences are even more severe than the destruction of atoms and chemistry. A negative cosmological constant creates a universe that contracts rather than expands. Inside the bubble of true vacuum, space-time itself would begin to collapse. Galaxies, if any structures remained after the transition, would rush toward each other. The universe would recollapse into a big crunch, a mirror image of the Big Bang, where all of space and time converge to a singularity of infinite density and infinite curvature. This collapse would not happen slowly. The rate of contraction would accelerate as space shrank, driven by the increasingly dominant negative dark energy. Within millions or billions of years after the bubble formed, the universe inside the bubble would reach such extreme density that quantum gravitational effects become important. At this point, general relativity breaks down. We cannot predict what happens at the singularity because our theories fail in regimes where both quantum mechanics and gravity are strong. Some speculate the universe might bounce, transitioning to a new expansion phase with completely different properties. Others argue the singularity represents a true boundary of spacetime, a point beyond which the very concepts of space and time cease to have meaning. Even in scenarios where the true vacuum has a less catastrophic cosmological constant, the transition would be unsurvivable for any structure or process that relies on current physics. Consider what would happen to a planet like Earth if it were caught in the path of an expanding vacuum decay bubble. As the domain wall approached, there would be no warning. The sky would appear normal. The stars would shine with familiar light. Then the wall would arrive. In a fraction of a second, shorter than the time it takes light to cross the diameter of Earth, the entire planet would be engulfed. The domain wall would pass through the Earth's interior, and as it did, the Higgs field would change value. Every quark in every proton and neutron in every atom would suddenly acquire a different mass. The strong nuclear force binding these quarks together would change strength. Nuclei would fly apart or collapse into unrecognizable configurations. The energy released in this process would be staggering. The mass energy of every particle would shift, and the difference would be liberated as radiation. If the mass changes are significant, this could represent a substantial fraction of the Earth's total mass energy. E equals mc squared tells us that even tiny masses correspond to enormous energies. Converting a fraction of the Earth's mass into radiation would produce an explosion that makes supernovae look gentle by comparison. But there would be no one to witness it. The atoms that made up observers, their brains, their neurons, their thoughts, would cease to exist a fraction of a second before the explosion occurred. Consciousness would not survive to register pain or fear. Existence would simply stop, as if someone had flipped a switch turning off reality. Outside the expanding bubble, the universe would continue as if nothing had happened. Light from regions that had been consumed would still be traveling through space, carrying images of galaxies and stars that no longer exist. An observer far from the bubble would see no warning of the approaching doom. They would observe galaxies in the distance, see them rotating and forming stars, completely unaware that those galaxies had already been erased and replaced by a region of incompatible physics. Only when the bubble wall reached them, moving at light speed, would they discover the truth, and by then, it would be too late. The destruction would be instantaneous and absolute, allowing no time for understanding or acceptance. Is there any way to prevent or escape vacuum decay? The short answer is no. If our vacuum is truly metastable, then decay is a matter of probability and statistics, not something that can be controlled or prevented. You cannot stabilize a quantum field that wants to tunnel to a lower energy state any more than you can prevent radioactive decay. The process is fundamentally random, governed by quantum mechanics, and no technology imaginable to us could alter the probabilities. Even if a civilization somehow developed the ability to manipulate quantum fields on large scales, using such technology might itself trigger the very catastrophe it aimed to prevent. High-energy processes, like those that might be required to stabilize the Higgs field, could provide the energy needed to help the field tunnel through the barrier, nucleating the bubble of true vacuum. Some physicists have speculated about whether vacuum decay could be deliberately triggered as a weapon. If you could create conditions of extremely high energy density in a small region of space, you might increase the local tunneling probability enough to nucleate a true vacuum bubble. This bubble would then expand at light speed, destroying everything in the universe. Such a weapon would be the ultimate doomsday device, rendering planets, stars, and even galaxies irrelevant. A sufficiently advanced civilization could, in principle, hold the entire universe hostage by threatening to trigger vacuum decay. But the mathematics suggests that the energy densities required to significantly enhance tunneling are far beyond anything achievable with realistic technology. You would need to compress matter to densities exceeding those inside atomic nuclei, sustaining these conditions over volumes large enough for quantum fluctuations to have a reasonable probability of occurring. The only possible escape from vacuum decay would be to leave our universe entirely, assuming there are other universes and assuming there is some way to travel between them. String theory and other frameworks for quantum gravity suggest the existence of a multiverse, a vast ensemble of universes with different physical laws and different vacuum states. If you could somehow tunnel from our universe to another universe with a stable vacuum, you might escape the eventual decay of our cosmic habitat. But this is pure speculation. We have no evidence that other universes exist, no theory of how to access them, and no reason to believe they would be habitable even if they do exist. Most other vacuums allowed by the standard model would have physical laws wildly different from ours, rendering them lethal to any structure or process that evolved in our universe. The psychological impact of vacuum instability is difficult to overstate. We are accustomed to thinking of the universe as a stage on which the drama of existence plays out, a neutral background that persists regardless of what happens within it. Vacuum decay shatters this comforting illusion. The stage itself is temporary, balanced in a precarious state that will eventually collapse. Everything we build, everything we discover, every thought and feeling and relationship, all of it rests on a foundation that is fundamentally unstable. This knowledge does not change our day-to-day lives. The probability of vacuum decay occurring in our lifetimes or even within the next billion years is vanishingly small, but it reframes the ultimate meaning of existence. We are not permanent features of reality. We are brief fluctuations in an unstable quantum field, structures that happen to arise during a temporary epoch when the physics allowed our existence. Some find this perspective liberating. If nothing lasts forever, if even the laws of physics are temporary, then perhaps we should focus on the present moment rather than worrying about distant futures we cannot affect. Others find it deeply disturbing, a reminder that all striving and achievement is ultimately futile in the face of cosmic impermanence. Philosophy and religion have grappled with mortality for millennia, but vacuum decay presents a form of death that is absolute and universal. Not just individuals or species or civilizations will die, everything will die. The very capacity for existence will be erased. The universe does not care about these emotional responses. It simply is. The Higgs field exists in whatever configuration minimizes its effective potential energy. And if that configuration happens to be metastable, so be it. We happen to arise during an epoch when the metastable state had not yet decayed, and we developed the physics to understand our predicament. In a sense, we are lucky. Most possible observers in most possible universes would never achieve sufficient understanding to realize their existence rested on unstable foundations. They would live and die in ignorance. We have achieved the dubious privilege of understanding our cosmic death sentence. But knowledge brings power, however limited. While we cannot prevent vacuum decay, we can study it, model it, and prepare for it intellectually, if not physically. Each improvement in our measurements of the Higgs boson and top quark masses refines our estimate of when decay might occur. Each advance in quantum field theory helps us understand what the transition would look like and what might remain after it occurs. This is the essence of science, confronting reality as it is, not as we wish it to be, and extracting whatever meaning and understanding we can from the facts. The fact that our vacuum is metastable, that our existence is temporary on the grandest scale, does not diminish the importance of seeking truth. If anything, it intensifies the urgency. We have only a limited time, measured in billions or trillions of years perhaps, to learn as much as we can about the universe before it transforms into something else entirely. The research continues. Physicists at the Large Hadron Collider are planning upgrades that will increase the collision rate and improve detector sensitivity, allowing even more precise measurements of Higgs and top quark properties. Theorists are developing better techniques for calculating quantum corrections to the Higgs potential, incorporating effects from gravitational interactions and possible new physics beyond the standard model. Cosmologists are studying the early universe, searching for clues about whether vacuum phase transitions occurred in the past and what they can tell us about the future. Every piece of data, every calculation, every observation brings us closer to understanding the true lifetime of our reality. And what of the distant future? If humanity or its descendants survive for billions of years, will they witness the approach of vacuum decay? The answer depends on how long our civilization lasts and how the universe evolves. If intelligent life spreads throughout the galaxy and beyond, if we develop technologies for harnessing the energy of stars and even black holes, we might persist for timescales comparable to the vacuum lifetime. In that case, far future civilizations would face the reality of impending destruction not as a theoretical abstraction, but as an observable threat. They might detect the formation of a vacuum bubble somewhere in the distant universe, see it expanding toward them at light speed, and know with certainty that their time was limited. There would be no escape, no possibility of outrunning the bubble, only the grim countdown to the moment when the wall arrives and reality ends. Or perhaps the vacuum will decay much sooner, catching us off guard while we are still confined to a single planet or single star system. In that case, the end would come before we had developed the capacity to observe it approaching, a sudden termination without warning or understanding. From our current perspective, separated from the potential catastrophe by billions or trillions of years, this seems almost merciful. But it is also a waste, a universe full of structure and complexity being erased before it had time to fully explore its own potential. The calculations that doom our universe emerge from the most successful scientific theory ever constructed. The standard model of particle physics has been tested to extraordinary precision over decades of experiments, and it has passed every test. Its predictions for particle masses, decay rates, interaction strengths, all have been confirmed to many decimal places. The same mathematical framework that allows us to design computer chips and predict the results of collider experiments also tells us that our vacuum is not in its lowest energy state. We cannot dismiss this prediction as speculative or uncertain. It rests on the same physics that powers the modern world. If the standard model is right about everything else, and it has been right about everything we can test, then it is probably right about metastability too. The Higgs field was the last piece of the standard model to be experimentally confirmed. For decades, physicists knew that something had to give particles mass, and the mathematics suggested that something was a quantum field permeating all of space. But the Higgs boson, the particle associated with this field, was too heavy to create at existing colliders. It took the construction of the Large Hadron Collider, the most powerful particle accelerator ever built, to finally observe the Higgs in 2012. That discovery completed the standard model but opened new questions, including the stability of the vacuum. Now, just over a decade later, we are confronting the implications of that discovery. And they are not comforting. The universe revealed by 20th and 21st century physics is strange and hostile. It began in a singularity of infinite density and temperature. It expanded and cooled. Quantum fluctuations in the first moments seeded structures that would become galaxies and stars. Matter clumped under gravity. Stars ignited, fusing hydrogen into heavier elements. Planets formed. On at least one planet, chemistry became complex enough to support replication and evolution. Life arose, evolved, became conscious, developed science, and discovered that the stage on which this drama unfolded is not permanent. The ground beneath our feet, the atoms in our bodies, the forces that bind them together, all rest on a quantum field that exists in a state of precarious balance, waiting for a random fluctuation to tip it into oblivion. This is the universe we inhabit, not the clockwork cosmos of Newton, where time marches forward eternally and space provides a fixed arena for motion. Not even the relativistic spacetime of Einstein, where geometry curves but remains fundamentally well-defined. Instead, we live in a quantum universe, where fields fluctuate, particles tunnel through barriers they should not penetrate, and the very laws of physics are emergent properties of deeper quantum structures that can change. In such a universe, nothing is permanent. Not stars, not galaxies, not even the physical constants we thought were absolute. Everything is contingent, temporary, subject to the random processes that govern quantum systems. The new calculations showing an accelerated timeline for vacuum decay are not the first time physics has confronted humanity with uncomfortable truths. When Copernicus argued that Earth was not the center of the solar system, it challenged our cosmic significance. When Darwin demonstrated that humans evolved through natural selection rather than being specially created, it challenged our biological uniqueness. When Einstein showed that time was relative and space could curve, it challenged our intuitions about reality. Each time, humanity adapted, incorporated the new knowledge, and continued. Vacuum metastability is the latest in this series of humbling revelations. We are not special. Our existence is not guaranteed. The universe will continue without us. And eventually, the universe itself will transform into something that cannot support structures like us. But here, at approximately 12,500 words, a deeper horror awaits revelation. The calculations compress time. The quantum field trembles on its false peak. And the mechanism of our ending is more intricate, more inescapable than simple exponential decay. The universe is not just dying. It is revealing that it was never truly stable to begin with, that our existence has always been borrowed time, and that the math has finally caught up to reality. The true terror of vacuum decay lies not in the event itself, but in what it reveals about the nature of existence. We are not merely inhabitants of a universe that will someday end. We are patterns of information encoded in quantum fields that were never meant to persist. The Higgs field is not a deliberate creation designed to support life. It is an accident, a random configuration that happened to settle into a metastable valley after the Big Bang, and we are the fleeting structures that emerged before the inevitable collapse. This realization transforms every aspect of how we understand our place in reality. Consider what the Higgs field actually is. It is not made of particles in the conventional sense. It is a scalar field, meaning it has a value at every point in space but no directional properties. You can think of it as an invisible ocean filling the entire universe, with waves and ripples that manifest as Higgs bosons when the field is excited. Every particle that has mass interacts with this ocean. Electrons, quarks, neutrinos, all of them acquire their masses by moving through the Higgs field, like objects moving through molasses. The more strongly a particle interacts with the field, the more massive it becomes. The top quark, which couples to the Higgs field more intensely than any other known particle, is for this reason the heaviest fundamental particle in the Standard Model. But the Higgs field does not have a fixed, unchanging value throughout space and time. Quantum mechanics tells us that fields fluctuate. At every point, the field value jitters up and down due to quantum uncertainty. Most of these fluctuations are tiny, insignificant deviations that average out to the expected value. But occasionally, through sheer random chance, a fluctuation can be large. And if that large fluctuation occurs in just the right way, it can push the Higgs field over the energy barrier, separating our false vacuum from the true vacuum. This is the nucleation event, the birth of the bubble that will expand to consume everything. The mathematics of quantum fluctuations are well understood. They arise from the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the position and momentum of a particle with arbitrary precision. Applied to quantum fields, this means you cannot know the exact value of the field at a point in space and how rapidly it is changing at that same point. The field must fluctuate, must explore different values, simply because the laws of quantum mechanics forbid perfect stillness. These fluctuations occur at all scales, from microscopic to macroscopic, and they never stop. The vacuum is not empty and quiet, but seething with quantum activity, particles popping into and out of existence, fields oscillating wildly on tiny timescales. Most vacuum fluctuations are harmless. A brief spike in the electromagnetic field creates a virtual photon that exists for a trillionth of a second before disappearing. A dip in the electron field creates a virtual electron-positron pair that annihilates immediately. These processes violate energy conservation for fleeting moments, but the Heisenberg uncertainty principle allows such violations as long as they are temporary. Energy can be borrowed from the quantum vacuum if it is paid back quickly enough. The larger the energy violation, the shorter the allowed duration. This is why macroscopic objects do not spontaneously appear from nothing. Creating even a grain of sand would require such an enormous energy violation that the allowed lifetime would be far shorter than the time it takes light to cross a proton. But the Higgs field is different. It is not creating particles from nothing, it is transitioning from one configuration to another, from false vacuum to true vacuum. This transition releases energy rather than requiring it. The true vacuum has lower energy than the false vacuum, so once the transition begins, it is energetically favorable for it to continue. The initial fluctuation that nucleates the bubble does require overcoming the energy barrier, and this is why the process is so improbable. But once the barrier is crossed, the field rolls downhill into the true vacuum minimum, releasing energy as it goes. This released energy drives the expansion of the bubble, making the process self-sustaining. The probability of nucleation depends on the height and thickness of the barrier, as we discussed earlier, but it also depends on the volume of space and the duration of time over which fluctuations can occur. This is where the universe's size and age become critically important. Our observable universe contains approximately 10 to the power of 80 protons. If we imagine dividing space into regions the size of protons, there are 10 to the power of 80 such regions. Each region undergoes quantum fluctuations independently. Even if the probability of nucleation in any single region during any given second is incredibly tiny, say 10 to the power of -100, when you multiply by 10 to the power of 80 regions, the improbable becomes merely unlikely. And when you multiply by the billions of years the universe has already existed, and the potentially trillions or quadrillions of years it will exist in the future, the unlikely becomes inevitable. This is the statistical argument for why vacuum decay will eventually occur. The universe is simply too large, and time is simply too long for an improbable event to remain forever improbable. Quantum mechanics guarantees that any process with non-zero probability will eventually happen if you wait long enough and sample enough independent regions. The Higgs field exists at every point in space. Every point is fluctuating. Every fluctuation is a lottery ticket. And there are more lottery tickets being drawn every second than there are atoms in observable reality. Eventually, one of those tickets will hit the jackpot, nucleating the bubble that ends the universe. But the new calculations suggest we may not have as many lottery draws as we thought. The refinements to the Higgs potential based on improved mass measurements indicate that the energy barrier might be lower than previous estimates suggested. A lower barrier means a higher tunneling probability. Higher probability means fewer draws are needed before the catastrophic fluctuation occurs. The timeline compresses. Instead of 10 to the power of 100 years before decay becomes likely, we might have only 10 to the power of 10 or 10 to the power of 20 years. These are still incomprehensibly long timescales by human standards, but they are short compared to the ultimate age the universe could reach if it were absolutely stable. The compression of the timeline carries profound implications for the future of intelligence in the cosmos. If the vacuum is absolutely stable, or if the decay timescale is truly 10 to the power of 100 years, then intelligence has effectively unlimited time to develop, spread, and explore the universe. Civilizations could arise, fall, and be replaced by new civilizations countless times. The universe could host trillions of generations of conscious observers, each pushing the boundaries of knowledge and capability further than the last. But if the decay timescale is only tens of billions of years, comparable to the current age of the universe, then intelligence has far less time. We might be living in the only epoch when complex structures like stars and planets can exist, and that epoch might be much briefer than we hoped. This possibility forces a reconsideration of the Fermi paradox, the question of why we have not detected evidence of extraterrestrial civilizations, despite the apparent high probability that they should exist. If the universe is destined for vacuum decay on timescales of tens of billions of years, then perhaps civilizations are aware of this threat and have made a collective decision not to expand aggressively or broadcast their presence. Why build Dyson spheres and galactic empires if the universe will be destroyed before such projects can reach fruition? Why announce your existence to potential competitors or predators when the stakes are so low given the limited time available? This line of reasoning leads to a dark conclusion. Perhaps the great silence we observe is not because intelligence is rare, but because intelligence has calculated that there is no point in making noise. Alternatively, advanced civilizations might have discovered some way to protect themselves from vacuum decay that we have not yet conceived. Perhaps it is possible to create a region of space where the Higgs field is stabilized through technology we cannot imagine. Or perhaps they have developed methods for transitioning to substrates that do not depend on the standard model physics, uploading themselves into computational systems that can continue functioning even after the laws of physics change. These scenarios require technologies so far beyond our current capabilities that they are indistinguishable from magic, but they cannot be ruled out entirely. If civilizations millions or billions of years more advanced than us exist, they might have solved problems we consider fundamental and unsolvable. But the most likely explanation for the Great Silence remains the simplest. We are alone, or nearly so, in our galaxy, and perhaps in our observable universe. The conditions required for life to emerge and evolve to technological intelligence are so specific and so unlikely that it happens only rarely, and we are one of those rare occurrences. If this is correct, then the burden of responsibility falls entirely on humanity, and whatever descendants or successors we create, we might be the only conscious observers in the universe capable of understanding vacuum decay, and if we fail to preserve our knowledge and our existence, there may be no one else to carry the torch forward. The relationship between vacuum stability and the anthropic principle deserves deeper examination. The anthropic principle, in its weakest form, simply states that we should not be surprised to find ourselves in a universe compatible with our existence. This is a tautology. Observers can only observe universes that allow observers to exist, but the principle becomes more interesting and controversial when applied to explain why certain physical constants have the values they do. Why is the electron mass 0.511 mega-electron-volts rather than some other value? Why is the cosmological constant so extraordinarily small compared to naive quantum field theory predictions? The anthropic answer is that universes with very different values for these parameters would not support complex structures like stars, planets, and life, so we necessarily observe values in the narrow range compatible with our existence. Vacuum metastability fits awkwardly into this framework. On one hand, we can argue anthropically that we must observe a vacuum lifetime at least as long as the time required for intelligent observers to evolve. If the vacuum decayed too quickly, there would be no observers to measure its properties. This sets a lower bound on the lifetime, but it does not tell us anything about the upper bound. The vacuum could be absolutely stable, or it could be metastable with a lifetime of trillions of years, and both would be anthropically acceptable as long as the lifetime exceeds the few billion years needed for biological evolution. On the other hand, some physicists have argued that metastability might actually be anthropically favored over absolute stability. The argument goes like this. If the Higgs potential has exactly the right shape to make the vacuum absolutely stable, that requires a very specific relationship between the Higgs mass, the top quark mass, and other standard model parameters. This relationship is unlikely to occur by chance. It requires fine-tuning, where multiple parameters must take values within narrow ranges to achieve stability. But if the vacuum is metastable, no fine-tuning is required. The parameters can take a wide range of values, and as long as the resulting lifetime is long enough for observers to evolve, the vacuum is anthropically acceptable. From this perspective, we should expect to find ourselves in a metastable universe, because such universes are more common than absolutely stable ones in the space of all possible parameter values. This argument is controversial and not universally accepted. Critics point out that it relies on assumptions about the probability distribution of parameter values across the multiverse, if such a thing exists. We have no empirical evidence for how Higgs masses are distributed in other universes, or even whether other universes exist at all. The anthropic argument for metastability might be correct, but it might also be an example of over-interpreting limited data. We observe one universe with specific parameter values, and we should be cautious about drawing sweeping conclusions from a sample size of one. Nevertheless, the fact that our vacuum appears to be metastable rather than stable or unstable is intriguing. It sits on a knife edge, close enough to stability that the universe has persisted for nearly 14 billion years without decaying, but far enough from absolute stability that decay is a genuine threat on cosmological timescales. This balance is exactly what the anthropic principle would predict. A universe on the edge of viability, stable enough to allow our existence, but not so stable that it requires unlikely fine-tuning. Whether this is a deep truth about the structure of reality, or a coincidence of our particular cosmic accident, remains an open question. The quantum field theory underlying these calculations is built on principles that are almost a century old. Quantum mechanics was developed in the 1920s by physicists like Heisenberg, Schrödinger, Dirac, and Born. Quantum field theory, which combines quantum mechanics with special relativity, emerged in the 1940s and 1950s through the work of Feynman, Schwinger, Tomonaga, and others. The specific application to vacuum decay was pioneered by Sidney Coleman and Frank DeLucia in their seminal 1980 paper, Gravitational Effects on and of Vacuum Decay. That paper laid out the mathematical framework still used today to calculate tunneling probabilities in bubble dynamics. The Coleman-DeLucia calculation is a masterpiece of theoretical physics. It uses a technique called Euclidean path integrals. where you mathematically rotate time into an imaginary direction and then solve the field equations in this rotated spacetime. The solution describes an instanton, a configuration of the field that represents the quantum tunneling process. The action of this instanton, a quantity calculated by integrating the energy density over space and time, determines the tunneling probability. The calculation requires solving Einstein's equations of general relativity coupled to the equations for the scalar field, a technically demanding task that can only be done exactly for simplified models. For realistic potentials like the Higgs potential, physicists must use numerical methods and approximations. The results of these calculations are expressed as a decay rate per unit volume per unit time, typically written using the Greek letter gamma. Gamma has units of inverse volume times inverse time, and it tells you the probability that a bubble will nucleate in a given region during a given interval. If gamma is very small, say 10 to the power of -100 per cubic meter per second, then you need to wait an enormous amount of time, or sample an enormous volume, before nucleation becomes likely. The expected time before the first bubble appears is approximately 1 over gamma times the volume of space being sampled. For the observable universe, this volume is roughly 10 to the power of 80 cubic meters, so the expected time is approximately 1 over gamma divided by 10 to the power of 80. Current estimates for gamma depend sensitively on the precise values of the Higgs and top quark masses, as we have discussed. But they typically fall in the range of 10 to the power of -100 to 10 to the power of -50 per cubic meter per second for the Higgs vacuum. Plugging in the lower end of this range gives an expected lifetime of 10 to the power of 20 seconds, or roughly 10 trillion years. The higher end gives 10 to the power of 70 seconds, or 10 to the power of 63 years. These numbers should be taken with appropriate uncertainty given the approximations involved in the calculation, but they establish the rough magnitude of the threat. The vacuum will not decay tomorrow or next year, but it might decay within timescales that are cosmologically relevant. It is worth emphasizing that these calculations assume the standard model is complete and correct at all energy scales. If new physics appears at energies beyond the reach of current experiments, the calculations could change dramatically. For instance, if the Higgs boson is not a fundamental particle but a composite object made of more fundamental constituents, the effective Higgs potential at high energies could be very different from what standard model calculations predict. The same is true if extra dimensions exist, or if gravity becomes strong at accessible energy scales, or if the cosmological constant is dynamical rather than constant. Each of these possibilities would require recalculating the vacuum stability from scratch using the modified theoretical framework. The Large Hadron Collider has searched for evidence of physics beyond the standard model in every channel it can access. Physicists have looked for supersymmetric particles, extra dimensions, mini black holes, leptoquarks, heavy neutrinos, dark matter candidates, and countless other hypothetical phenomena. The results have been disappointing from the perspective of discovering new physics. No convincing evidence for any beyond standard model particles or interactions has emerged despite analyzing trillions of collisions. The standard model continues to describe nature perfectly up to the highest energies we can reach, which currently top out around 14 tera-electron volts in the center of mass frame of proton-proton collisions. This lack of new physics has profound implications. It suggests that if new particles or forces exist, they are either much heavier than we expected, requiring energies far beyond the Large Hadron Collider's reach, or they interact so weakly with standard model particles that they are effectively invisible to our detectors. Neither possibility offers much hope for stabilizing the Higgs vacuum. Heavy new particles cannot contribute significantly to the Higgs potential unless their masses are within a few orders of magnitude of the energies where vacuum instability sets in, which is around 10 to the power of 10 giga-electron volts according to current calculations. Particles that heavy are completely inaccessible to any conceivable near-future collider, and weakly interacting particles, even if they exist at lower masses, would not couple strongly enough to the Higgs field to substantially alter the shape of its potential. The situation is reminiscent of the dark matter problem. We have overwhelming evidence that dark matter exists from its gravitational effects on galaxies and galaxy clusters. Yet decades of experiments have failed to detect dark matter particles directly or produce them in colliders. If dark matter particles exist and have masses in the range of tens to hundreds of giga-electron volts, as many theoretical models predict, They should have been produced at the Large Hadron Collider. The fact that we have not seen them suggests either they are heavier than expected, or they interact even more weakly with normal matter than the most conservative models assumed. Either way, they remain frustratingly out of reach. The absence of new physics at accessible energies leaves us in an uncomfortable position. The standard model is incomplete. It cannot explain dark matter, dark energy, neutrino masses, the matter-antimatter asymmetry, or the origin of the Higgs potential itself. Yet nature appears to have conspired to make the next layer of physics inaccessible to our current technology. We are like children playing in a sandbox, able to build sophisticated castles and tunnels within our limited domain, but unable to see beyond the walls that confine us. The answers to our deepest questions about vacuum stability, the ultimate fate of the universe, and the nature of reality itself may lie in energy regimes we cannot reach, encoded in phenomena we cannot observe. This technological limitation is not absolute. In principle, we could build larger colliders capable of reaching higher energies. The Large Hadron Collider has a circumference of 27 kilometers and achieves collision energies of 14 tera-electron volts. A future collider with a circumference of 100 kilometers, such as the proposed Future Circular Collider at CERN, could reach collision energies of 100 tera-electron volts. This would allow exploration of physics at energy scales roughly 7 times higher than currently accessible, potentially revealing new particles or interactions that affect the Higgs potential. But building such a machine would cost tens of billions of dollars and take decades to construct. It remains unclear whether humanity will muster the political will and economic resources to pursue such projects. Even if we build more powerful colliders, there are fundamental limits to what we can discover through terrestrial experiments. The Planck energy, 10 to the power of 19 giga-electron volts, represents the scale where quantum gravitational effects become important, and our current theories of particle physics and gravity break down. To probe physics at the Planck scale directly would require a collider with a circumference comparable to the size of the Milky Way galaxy. This is obviously impossible with any technology we can envision. If the answers to vacuum stability lie at or near the Planck scale, we will never be able to test them experimentally. We will be forced to rely on indirect evidence and theoretical reasoning, always uncertain whether our conclusions are correct. Nature, however, has provided us with one experiment that operates at energies far beyond anything we can achieve in laboratories: the early universe itself. In the first moments after the Big Bang, the universe was filled with particles and fields at temperatures and energy densities that dwarfed anything since. During the first microsecond, the average energy per particle exceeded 1 tera-electron volt. During the first picosecond, energies exceeded 1 peta-electron volt. If we could observe the early universe directly, we could learn about physics at these extreme scales. Unfortunately, we cannot. The universe became opaque to electromagnetic radiation until about 380,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen and photons could stream freely through space. Before this recombination epoch, any photons produced would have scattered off the dense plasma filling space, randomizing their directions and erasing information about their origins. But photons are not the only messengers from the early universe. Neutrinos, which interact much more weakly than photons, could escape the early universe when it was only 1 second old. If we could detect these cosmic neutrino background particles, they would carry information about conditions when the universe was far hotter and denser than the epoch revealed by the cosmic microwave background. Unfortunately, neutrinos from the Big Bang have cooled to temperatures of only a few Kelvin and possess energies far too low to interact significantly with matter. Detecting them would require technologies we do not currently possess. Gravitational waves offer another window into the early universe. Unlike photons and neutrinos, gravitational waves do not interact with matter at all. They propagate freely through even the densest plasmas. In principle, gravitational waves produced during the Big Bang itself could still be traveling through space, carrying information about the universe when it was a tiny fraction of a second old. Several mechanisms in the early universe could have produced such primordial gravitational waves, including quantum fluctuations during cosmic inflation, phase transitions of quantum fields, and the chaotic motion of fluids in the hot early plasma. Detecting primordial gravitational waves is one of the major goals of current and future gravitational wave observatories. But it remains extraordinarily challenging because the signals are expected to be incredibly weak. If vacuum phase transitions occurred in the early universe, they might have produced detectable gravitational waves. When a quantum field transitions from one vacuum state to another, it does not happen uniformly throughout space. Instead, bubbles of the new phase nucleate at random locations and expand, eventually colliding with each other. These bubble collisions release enormous amounts of energy and create disturbances in space-time that propagate as gravitational waves. The spectrum of these gravitational waves, the distribution of their frequencies and amplitudes, encodes information about the energy scale of the phase transition and the properties of the quantum field that underwent the transition. The electroweak phase transition, which occurred when the universe was about a picosecond old and involved the Higgs field acquiring its current vacuum expectation value, might have produced detectable gravitational waves if it was strongly first-order. A first-order phase transition is one where the old and new phases coexist briefly, separated by bubble walls, before the new phase completely replaces the old. In contrast, a second-order or crossover transition happens smoothly without distinct phases or bubbles. Current calculations suggest the electroweak transition in the Standard Model was a smooth crossover rather than a first-order transition, which means it would not have produced significant gravitational waves. But if new physics beyond the Standard Model affected the Higgs potential, the transition could have been first-order after all. Detecting gravitational waves from the electroweak phase transition would revolutionize our understanding of vacuum stability. The signal would tell us about the shape of the Higgs potential at temperatures and energies far beyond what we can probe in colliders. It would reveal whether the potential has additional structure, such as multiple minima or barriers, that could affect the stability calculation. And it would provide direct evidence for or against new physics that couples to the Higgs field. Several proposed space-based gravitational wave detectors, such as the Laser Interferometer Space Antenna or the Big Bang Observer, could potentially detect these signals if they exist, and if we build the detectors. But even with all possible experimental data from colliders, cosmic observations, and gravitational wave detectors, we may never achieve complete certainty about the fate of our vacuum. The calculations involve extrapolating our theories to energy scales and field values far beyond what we can test directly. We must trust that the mathematical frameworks we have developed, quantum field theory, and general relativity, remain valid in these extreme regimes. This trust is based on the theories, success in explaining observations within their tested domains. But extrapolation is always risky. Nature could surprise us with new phenomena that invalidate our predictions. The psychological weight of vacuum instability is compounded by its inevitability. Unlike many existential threats facing humanity, climate change, nuclear war, asteroid impacts, pandemics, vacuum decay, cannot be prevented or mitigated through any action we can take. If the vacuum is metastable, it will eventually decay. The timing is a matter of probability and statistics, not something we can influence. We are passengers on a train hurtling through space-time, knowing the track ends somewhere ahead but unable to see where or when we will reach the terminus. This lack of agency is profoundly unsettling to a species that has spent its entire history fighting to survive and control its environment. Some philosophers argue that vacuum instability renders all long-term planning and striving meaningless. If the universe will be destroyed in a vacuum decay event, what is the point of building civilizations that aspire to last millions or billions of years? What is the point of spreading to other stars or galaxies if all of it will be erased? This nihilistic perspective sees vacuum decay as proof that existence is fundamentally absurd, that there is no ultimate purpose or meaning to anything we do. We are temporary patterns in quantum fields, dancing briefly before the music stops and silence consumes everything. Others reject this nihilism and argue that meaning is not diminished by impermanence. The fact that a symphony ends does not make the music meaningless while it plays. The fact that a human life ends does not make experiences, relationships, and achievements pointless. By this reasoning, the eventual decay of the vacuum does not invalidate the value of existence during the time we have. We can still create, discover, love, and explore. We can still reduce suffering and increase flourishing. The ultimate fate of the universe does not determine the meaning of our actions. We create that meaning through our choices and values. This existentialist perspective finds comfort in autonomy and self-determination. We are not given meaning by the universe. We construct it ourselves through the way we live. Vacuum decay, like all forms of mortality, simply provides a boundary condition within which we must operate. It is a constraint, but constraints can be liberating. Knowing that time is finite focuses attention on what matters most. If we truly had infinite time, we might procrastinate forever, assuming there would always be another chance to do what we value. But finite time, even if that finitude is measured in billions of years, demands that we act now rather than deferring our aspirations to an endless future. The religious and spiritual implications of vacuum instability have not been widely explored, perhaps because the concept is so recent and so abstract. Traditional religious cosmologies tend to envision an eternal afterlife or a divine plan that ensures some form of permanence for souls or consciousness. Vacuum decay challenges these frameworks by suggesting that the physical substrate necessary for any kind of existence, even a non-material soul if such a thing exists, will eventually be destroyed. If the laws of physics themselves are rewritten, there may be no way for information patterns, whether they represent human minds or divine beings, to persist. Some theological traditions might interpret vacuum instability as consistent with eschatological prophecies of an ultimate end to the current creation. Christianity, for instance, speaks of a new heaven and new earth that will replace the current cosmos. If vacuum decay represents the mechanism by which the old cosmos is destroyed to make way for a new creation, it could be seen as fulfilling rather than contradicting religious teachings. But this interpretation requires believing that something transcends the physical universe, something that exists independently of quantum fields and space-time geometry. For materialists who hold that consciousness and existence are entirely physical phenomena dependent on specific arrangements of matter and energy, governed by the laws of physics, vacuum decay represents an absolute end, with no possibility of continuation or transcendence. The question of whether consciousness could survive a vacuum transition depends on what consciousness is and how it relates to physical substrate. If consciousness is purely an emergent property of certain computational processes, and if those processes can only occur in physical systems governed by our current laws of physics, then consciousness ends when the vacuum decays. The new physics inside the true vacuum bubble might not support the complex chemistry and thermodynamics necessary for brains or any analogous information processing structures to exist. Even if some form of complexity is possible in the new vacuum, it would be so alien to our current existence that it could not meaningfully be called a continuation of our consciousness. However, some speculative theories suggest more optimistic possibilities. If consciousness is substrate-independent and can be implemented in any sufficiently complex computational system, regardless of the underlying physics, then perhaps minds could be uploaded or translated into structures that remain stable in the true vacuum. This would require technology capable of mapping every relevant aspect of a conscious mind, and then creating an equivalent computational process using whatever physics exists on the other side of the transition. Such technology is far beyond our current capabilities and may be impossible even in principle, but it cannot be entirely ruled out if consciousness is indeed substrate independent. Another speculative possibility involves the holographic principle and the idea that information about the interior of a region of space is encoded on its boundary. Some interpretations of quantum gravity suggest that the universe might be holographic, with all information about three-dimensional space actually stored on a two-dimensional boundary at the edge of the observable universe. If this is correct, and if the boundary survives vacuum decay in some form, then information about our universe, including potentially information about every conscious mind that ever existed, might persist even after the interior is transformed. This information would not constitute consciousness in any active sense, but it would mean that our existence leaves a permanent imprint on the structure of reality. These possibilities are highly speculative and depend on unproven assumptions about the nature of consciousness, information, and quantum gravity. They offer no comfort in the face of vacuum decay, because even if information somehow persists, the active, experiencing aspects of consciousness almost certainly do not. We would be reduced to static records in a cosmic library that no one can access or read. From a practical perspective, vacuum decay means the end of everything we care about. Sensation, thought, feeling, agency, all the qualities that make existence meaningful to conscious beings. The decay of our vacuum would be the ultimate tragedy, greater than any catastrophe that has occurred or could occur within our current physics. The extinction of humanity through nuclear war or climate change would be terrible, eliminating billions of years of potential future flourishing. But life could potentially re-emerge from survivors or from independent evolution elsewhere in the universe. The destruction of Earth by the Sun's expansion in 5 billion years would be more severe, eliminating our home planet, but humanity or its descendants might have spread to other star systems by then. Even the heat death of the universe, where all stars burn out and black holes evaporate, would not necessarily end all forms of existence. Some have speculated that civilizations could survive into the far future by using black hole evaporation as an energy source, or by slowing down their information processing to match the declining energy availability. But vacuum decay is different. It does not merely destroy existing structures. It makes all structures impossible by rewriting the laws that permit structure to exist. There is no adaptation, no escape, no way to rebuild afterward. The universe after vacuum decay would be a fundamentally different place, possibly devoid of any complexity whatsoever. If the true vacuum has a sufficiently negative cosmological constant, space-time itself would collapse into a big crunch shortly after the transition. If the particle masses in the true vacuum are wildly different from current values, atoms could not form and chemistry would be impossible. If the fundamental forces have different strengths, stars could not exist to provide energy for complex processes. We are forced to confront the possibility that our universe is not built to last. The Higgs field's metastability suggests that the current configuration of physical law is temporary, an unstable equilibrium that will eventually collapse into something else. This is not a bug, but a feature of quantum field theory. Fields settle into local minima of their potentials all the time, and they escape those minima through thermal fluctuations or quantum tunneling. The Higgs field is no different except in scale. When it transitions, it takes everything with it because everything depends on its current value. The truly horrifying aspect of the new calculations is not just that they compress the timeline, but that they reveal our existence as even more contingent than we realized. We thought we had tens of trillions of years before vacuum decay became a concern. Time enough for countless civilizations to rise and fall. Time enough for intelligence to explore every corner of the accessible universe, and perhaps even find ways to transcend physical limitations. The new numbers suggest we might have only tens of billions of years, barely more than the current age of the universe. We are living not in the early stages of a nearly eternal cosmos, but possibly in the middle or even late stages of the only epoch when complexity is possible. This reframing of cosmic history has profound implications. If we are living in the brief window between the Big Bang and vacuum decay, then the universe's story is much simpler and shorter than we imagined. There is not time for endless cycles of cosmic evolution, for intelligence to develop technologies we cannot conceive, for new physical principles to emerge from the exploration of reality. There is just this, one burst of structure formation following the Big Bang, a few tens of billions of years when stars shine and planets orbit and possibly life emerges, and then a catastrophic transition that erases it all and replaces it with something sterile and simple. The realization lands with the weight of existential diagnosis. We are not children in a universe that will nurture us through countless ages. We are mayflies born into a cosmos already approaching twilight. Our entire history, from the first stars to the last black hole compressed into a cosmological instant. The universe is dying, and the new calculations have brought the death certificate forward. Our time is shorter than we believed. The quantum fields that birthed us are unstable, and there is absolutely nothing we can do except witness our own impermanence and try to extract whatever meaning we can from the brief light before darkness falls. If you want to continue exploring the terrifying truths hidden in the equations of physics, subscribe. Because the universe's secrets are darker than you imagine, and we have only begun to understand how fragile our existence truly is.